Space is vast. Since the launch of Sputnik, we've been sending things into space, and it's getting crowded. We track about 50,000 objects per night, larger than the size of a grapefruit. And then there's probably another 300 to 600,000 objects larger than the size of a golf ball. We want to ensure that the satellites we're launching are not going to be impacted by these debris. So we have to start tracking very small objects as well. Even a tiny fleck of paint can destroy a spacecraft. So when I say objects, you have to think about everything that is associated with a rocket launch. You have things like boosters, you have satellites, you have the payload shroud. In addition, space is no longer a benign environment. For a vast majority of the space age, we thought space was there for the good of humanity, but that's no longer the case. Space is a contested environment. We have our adversaries who regularly challenge our access to space. Given this, having a formal center at the University of Arizona that focuses on space safety, security, and sustainability is an important thing. The next grand challenge for us, how we manage the traffic we have around the Earth and eventually around the Moon. Space domain awareness is really challenging, and it's challenging because you have to bring in multiple disciplines to enable it. One is physical observations, whether it's in the lab or with the telescope. The other thing is modeling and simulation. So this is including developing pipelines, using machine learning and AI algorithms to enable our observations.
Our focus is algorithms and cyber infrastructures that can enable end-to-end data processing capabilities. You try to generate actionable intelligence, information that can support your decision. More specifically, you want to know what the object is doing.
The biggest challenge is if you go look at two satellites through a telescope, they just look like two dots. You can't tell which one is ours and which one is the bad guys. You have to have some other information. This technique is called spectroscopy. To do that, we take the light reflected off the satellite and we split it to different colors. And we analyze the colors reflected off the satellite to understand whose satellite it is. Kind of like fingerprint. The next step is sensors. We have a facility down at Biosphere 2 where we track these satellites. We not only find their orbits, we find out how fast they spin, we also find out what they're made of. So a telescope from the University of Hawaii discovered an object in September of 2020. Soon we realized it's going to come really close to the Earth, and in November of 2020, it would get captured by the Earth temporarily. And that gave a pause to astronomers. That basically means it either came out of the Earth or it came off the Moon. So then they ran the orbit back in time and realized that in 1966, this object was very close to the Earth. And looking at the launch manifest, what was happening in 1966, they realized that there was a launch towards the Moon of a spacecraft called Surveyor 2. So that's where our team came into the picture because we have this capability to understand what things are made of.
So one of the first steps was to use the biggest telescopes that we have access to get some basic color data that we can use for a rough spectrum of the object. That tells us, do we think this is a rock from outer space or is it a rocket that may have come from Earth? So we had some ideas that this object was related to an Atlas Centaur launch. The way that we could kind of confirm that is looking at the handful of these objects that were launched from the same time period that are still orbiting the Earth to this day.
In a case like 2020 SO, what we would do is take our unknown spacecraft and we use known spacecraft that we believe that it could be and look at its spectrum and look at the features of that spectrum and use that to help us identify the spacecraft. Comparing the spectrum of the known to the unknown. It's a good first step because it allows us to see if we're even on the right idea of what it could be.
So we've been studying this object for a couple of months, but a lot more information comes from the near-infrared wavelengths of light. We had a brief window where the object got captured in the Earth-Moon system and was close enough and bright enough where we could use NASA's infrared telescope facility, which is in Hawaii, and we could track it and get these infrared spectra where we were able to fingerprint the materials on the spacecraft. And then later we were able to match that to spectra that we take in the laboratory.
We got spectra on multiple nights, and in between we were able to talk to a historian at Johnson Space Center who identified stainless steel and polyvinyl fluoride as sort of the two biggest components on Centaur rockets from the 1970s. I was able to find commercially available pieces, and both those matched the 2020 SO spectrum spot on. This definitively showed that 2020 SO was a rocket body from the 1970s and likely the Surveyor launch vehicle.
I think it was in February of 2015, Catalina Sky Survey picked up an object somewhat near the moon. It was realized that this object was actually orbiting the Earth, not the sun. No one really cared about it until we found out it was going to hit the moon. John Giorgini was looking at the trajectory of the Discover mission that we thought it belonged to, and that was launched on a Falcon 9 rocket body. And he said, well, they didn't really go particularly close to the moon, so it was very unlikely that it was actually that Falcon 9. And that kind of meant off to the races to figure out what it was.
When we realized that this was not Falcon 9, I knew we had to bring in our A-team to crack this mystery. So I called Adam and I told him, we're going to do the same thing we did with 2020 SO.
I was able to help collect the spectral observations so that we could compare the mystery object to objects that we observed around Earth. And when we looked at this mystery object headed towards the moon, it had a kind of redder spectral slope, so that matches the Chinese rocket bodies that we were able to observe orbiting the Earth.
Then I called Tanner and I said, try and identify the orbit and see if we can trace it back.
This is called orbit propagation, where you're actually integrating the equations of motion that describe how that object moves in space, and you're sending that backwards in time. If you look around that date for anything that was launched going towards the moon, the only candidate was the Chang'e 5 T1 mission. After we had gotten that clue, we put out a press release, and after that, the Chinese Foreign Ministry actually did a press release denying it, but the Chang'e 5 T1's rocket body was never found until we did this study. When the rocket body from the Chang'e 5 T1 mission actually impacted the moon, we had a very good estimate of where it was going to impact. So good, in fact, that the Lunar Reconnaissance Orbiter went over the area where it impacted to image it. And what they found was that instead of just a single crater left behind, there were actually two. This made us think that that rocket body actually had other instruments on it. This whole project was a great experience for our whole team at the Space4 Center to show what you actually can do with this type of data if you spend the time to go through it.
So it takes a whole ecosystem to do this work. And what we are blessed with here at the University of Arizona is that ecosystem. We're a world leader in astronomy, in planetary sciences, optical sciences, cyber infrastructure, space exploration. So we are bringing all these capabilities to the Space4 Center to ensure that our satellites leaving the Earth can operate around the moon safely for the foreseeable future.